Okay, welcome to this first lecture for Physical Geology, Geology 101 with Pima Community College for the spring of 2021. Welcome to everybody. Hopefully this will be a system that will work for you. It's not the normal in-class situation. As you know, for the last almost a year, we've been dealing with this pandemic, so we're making accommodations as we can to try to still provide the best learning experience possible. Philosophically, this is a little different and a little difficult for a physical science such as geology because geology is a very hands-on science. My understanding is you will be getting a sample kit here shortly that will let us be able to work through the labs together. It's not an ideal situation in my mind personally, but I think we'll be able to make it work. With that said, the syllabus is available online. Hopefully you have found that. I've posted it as well as a downloadable version of it. It may be better to use the downloadable version to access the book. I'm not sure. We're using a new book this year. It is a free online book, so there's some good news for you there. Not a $168 textbook. In terms of the way the class will work, we will have a degree of lecture, which will be provided mostly by videos. When we meet on the class days, it'll be for roughly about an hour, starting at about 6 p.m. using the Bongo virtual classroom online through the D2L. And then we can have one-on-one sessions afterwards for additional questions or additional help as needed. There will be some lab work, there will be testing, there will be a couple of virtual field trips that I have put into the schedule. Those are in there as in the next couple of weeks I'll develop the schedule in the D2L a little better with the assignments and whatnot and hopefully get that flushed out for you. So with that, please understand that the lectures that I give are going to cover basically the same material as the books, maybe in a slightly different order, slightly different viewpoint. So the lecture is really meant to help guide and focus your reading comprehension on the lecture, on the chapter. So my standing recommendation is, realistically speaking, whenever possible, please read the chapter before you listen to the lecture. Then come up with for the discussion, come to the class with questions for things that you didn't understand or things you want a further explanation on. That way I can answer those questions. Now, I will not sit here and insult anybody's intelligence and tell you there's no such thing as a stupid question. Having made a career of figuring out how to ask a stupid question of my teachers just for the fun of it, I know it can be done. However, if it's a question because you do not understand something, it by definition is not stupid. If it's you just trying to make a point or play a game, all right, then it can be stupid. But if you are trying to truly understand something or don't understand something, it's not a stupid question. So please feel free to ask questions. A little bit about myself. I've probably been a geologist at heart most of my life. First day of kindergarten, my teacher wanted to know what I wanted to be when I grew up, and I said I wanted to be a paleontologist, and I had to write it on the board for her to be able to look it up in the dictionary. My degrees are in geology and planetary science from Northern Arizona University and Brown University, respectively. I work for the Santa Cruz County Flood Control District, where I use my understanding of geology to help bring a better understanding about the nature of the floodplains and how those systems work. Beyond that, I want to talk to you today about Chapter 1, which is basically an introduction to geology. Call it Geology 100L. It's just a real simple overview of a lot of what we're going to be discussing and building up for the first, mostly half of this semester. So let's start by asking the question, what is geology? Well, if we look at the word, it can be broken up into two parts, geo and ology. Geo comes from the ancient Greek for earth, and ology comes from the ancient Greek for the study of. So it's the study of the earth. One of the definitions I've heard that I've really liked over the years is it's the study of everything in the universe that's not glowing or alive. I like to think of geology as the mother of all science, for the simple reason that the first tools man ever used outside of wood was rocks. And the different properties of the different rocks make the different rocks usable for different things. For example, volcanic glass, aka obsidian, is a material that when it's flaked properly, it can create edges that are very, very sharp. In fact, upwards of 10 times sharper than surgical steel. It's actually a prized use tool for certain surgical procedures because it leaves very little scarring and very fine scars. You would not want to use that to try to chop down a tree, however. Skin an animal? Yes. Chop a tree? No. You need something more sturdy, something harder, denser. So by looking at the rocks and figuring out their different properties, really, I think, kicked off our understanding of science. It's the mother of all science. So if we look at it based on the definitions we use today, geology is the science that pursues an understanding of the planet Earth. Now, we can break it up into two general fields of geology. There are many subcategories of geology, but there are two primary fields of geology. There is physical geology, which is looking at the materials comprising the planet, as well as understanding the processes that operate within the physical Earth itself, and working both below the surface and on the surface to shape the surface, to shape the features that we see, to create the materials that we see. The other is historical geology. Historical geology seeks an understanding of the origin of the Earth and its development through time. Now, the understanding of the Earth is challenging because the Earth is a dynamic system. It is not a static system. If we had a time machine and can jump back 40, 50,000 years and land back in the area, generally the landscape will look fairly similar. There will be a few key differences, but it will look generally similar. Go back a few million years, won't look anything like what we see today. So the Earth's process is dynamic. The Earth's system is constantly shaping and reshaping the surface of the Earth. Now, there are a number of reasons why we want to study geology in general. The interrelationship between people and the natural environment, especially with climate change, that is something that we really need to learn and understand better. We also look at it to help us understand natural hazards such as earthquakes or volcanoes or landslides. There's as well as resources. Most of what is around you right now is a resource with a geologic background. The wallboard that makes up your wall. Some of the plaster that's in it, mineral called gypsum, makes that up. Your computer has silicon in it, and gold or silver, other rare earth elements. Your car, natural gas, oil, gasoline, metals, all are components that we find in geology. We also look at it in terms of trying to help us understand world population growth and the impact that geology can have on that. One of the things that's been a big thing for a long period of time is that a large portion of the world's population live in areas that either have active volcanoes or active earthquake zones, or both. So that can have a major impact on world population, as well as environmental issues. We have things like supervolcanoes, where they do not erupt often, but when they do erupt, they can have a significant impact on the world itself, on its environment, and actually change the environment. So let's look at kind of like the science or the history of science to a degree, and the history of geology to a degree. The nature of the Earth has been a focus of study for millennia. It goes back as far as the early Greeks, who wrote on topics about gems and fossils and earthquakes and volcanoes, starting over 2,300 years ago. Aristotle himself is probably the most influential of the Greek philosophers. He was a student of Plato. He was a teacher to Sophocles and Alexander the Great, if I remember correctly. He wrote about deductive reasoning, the idea of making observations and coming to a logical conclusion for something. This is countered by the idea of inductive reasoning in science, which is making measurements and then coming to a conclusion based on those measurements. Very similar ideas and ways of approaching things slightly differently, but trying to use a logical system to understand things. Keep in mind that science is an objective system. It tries to be based on purely evidentiary materials, purely actual facts and information. It's not an intuitive system, which tends to be more emotional in nature. Between Aristotle and the Renaissance in Western civilizational history, there was the period called the Dark Ages, and science was all but lost in the West for that time. Thankfully, that science had been picked up and moved into the Middle Eastern cultures, especially the Arabic cultures, and it thrived there from roughly 800 AD to 1400 AD when the Renaissance began, and it began to make its way back into Western civilization. We saw a lot of different developments. Your book will talk about the work of Kepler and Copernicus and Galileo in the beginning of the Renaissance. We'll talk in the earlier stages of Ptolemy, who came up with the idea of what they call a geocentric model, where the Earth is the center of the universe and everything goes around the Earth. And it was Kepler, followed by Copernicus and Galileo, that showed that no, the sun is really the center and everything goes around the sun in a heliocentric model. And then it became that, well, the sun isn't actually the center of the universe. It's not even the center of the galaxy. So kind of showing our place in the universe as a whole. Now, for much of that period of time, the main idea of how things were shaped on the Earth was an idea called catastrophism. This was an idea put forth or articulated by Archbishop James Ussher in the mid-1600s, that basically the idea is that everything happens through catastrophe. Archbishop Ussher developed a history of the Earth based on the Bible, and he came up that the Bible was only a few thousand years old and had it formed on, I think it was September 4th at 4:30 p.m. Yeah, he actually did get somewhat that specific. I'm not joking. 4004 BC. Now, during the 17th and 18th centuries, the doctrine of catastrophism really strongly influenced science in general and philosophy in general. It was believed that catastrophes shaped the landscape. Like Noah's flood was responsible for much of the shape of the world that we see today. Features in mountains, canyons were caused by sudden worldwide disasters. In the 1700s, a revolution began with a Scottish natural philosopher by the name of James Hutton. James Hutton wrote The Theory of the Earth, and in that he had an idea. Now, the story goes as this. There was a beach in Scotland that Hutton was sitting at, having lunch. And he noticed in the beach, near his feet, at the edge of the water, ripple marks in the sand. And he noted that on the rocks he was sitting on, there were the same ripple marks in sandstone. but they were vertically oriented, not horizontally oriented. He realized at that point that if you had enough time, the processes that we see acting on the Earth today can actually account for the features we see in the rocks. All it takes is time. This began the concept of what we call deep time or geologic time. This became the principle that James Hutton put forth called uniformitarianism. Basically, it states that the present is the key to the past. And I like to add that the past is the key to the future. Prior to Hutton, no one demonstrated that the processes could or did last over a long period of time. Now, Hutton's work almost became forgotten until it was revived and republished in part in another book by Charles Lyell about almost a century later. I don't remember the exact date off the top of my head. But that really began to kick off what we now call modern geology. So from a scientific standpoint of the modern sciences, modern geology is not that new, but it's not that old either. Now, one of the things that this brings up is geologic time itself. For much of the history of modern geology, closing in on almost half now, we could not figure out when something happened. We could figure out the order of how things happened. For example, let's say I gave you a bunch of cards, and on those cards were depicted pictures at different stages of making a pizza. I'm pretty positive that almost everybody listening right now could put those pictures in the proper order for how the pizza was made. Okay, that is what we call relative dating. That's just putting things into their relative order, and we will spend an entire chapter on geologic time and geologic dating, so we'll get into this much deeper later. But there are different ideas that we use for that, such as the law of superposition, the principle of original horizontality, which were founded by Danish priest Nicholas Steno and others. Now, fast forward to the early 20th century, and we began to develop what we call absolute dating or radiometric dating, based on the fact that radioactive materials decay at a very specific rate, and we can measure the ratios of those materials, assuming that there's not been any significant disturbance or any disturbance in the material since it formed, and actually come up with a reasonably accurate idea of how old that material is. That has brought forth that instead of millions of years of time, we are dealing with billions of years of time for just the formation of the Earth, or since the formation of the Earth. So it gives you an idea about the magnitude of the scale of geologic time. It is very difficult to comprehend numbers that long or time that long. I mean, the 19 minutes I've spent talking right now might have seemed an eternity to some of you, but it's nothing in comparison to the length of a day. So as we move forward with science, we must keep in mind the nature of science, that it assumes that the natural world is consistent and predictable. The goal of science is to discover the underlying patterns in nature and use the knowledge to make predictions. We collect facts through observation and measurement. Now, one of the things that we have to keep in mind is that at this point right now, I want to make something very abundantly clear. Science does not actually prove anything. The scientific method, which we're about to discuss, is not set up for that. It's not designed for that. In fact, the one thing scientists want to have happen when possible, is to be proven wrong, to have something shown as wrong, because that means there's something else to learn. So let's get a few terms out of the way here. They're very, very important. They are testable. Literally, what I'm telling you right now will be testable. Okay, a couple of things that we need to keep in mind for vocabulary. First is the word hypothesis. A hypothesis is a tentative or untested explanation for an observed phenomena or observed facts of the natural world. A theory is a well-tested, widely accepted view that the scientific community agrees is the best explanation of certain observable facts or phenomena. In other words, it's a hypothesis that has survived scrutiny. That's a very important distinction from the way we use the word theory in everyday language. When somebody on TV says, I have a theory, they're actually using theory to mean they have an educated guess or an untested idea, aka in science, a hypothesis. So we have to be very careful about the use of the words theory and hypothesis in how we're using them. Another term to use is a paradigm. A paradigm is a theory that is held with a very high degree of confidence because it explains a large number of interrelated aspects of the natural world. Gravity is pretty much a paradigm at this point. Okay, so let's talk about the scientific method and how these terms really kind of interact in it. First and foremost, we start with an observation or a question. Why does something happen? Let's stick with gravity. Why does this little jar fall when I let go of it? Okay, so we gather facts, we gather observations, and we formulate a hypothesis, an idea. Sir Isaac Newton said that there must be a force acting on this jar caused by the earth. So there's a force of attraction between masses, and it falls. Tests were developed to test that. One test involved taking two small metallic balls and hanging them very precisely in an enclosure to eliminate influences from air movement and whatnot. And they looked at the two masses. Now, if Newton was generally correct and there's a force of attraction between the two, then the distance between the two should be slightly smaller than the distance they were set at. And lo and behold, when that test is run, that is what is observed. So there appears to be a force of attraction between objects. And you can follow along the math if you understand a little bit of calculus, which was actually developed by Sir Isaac Newton to explain physics, which starts with gravity. You can actually follow that math along and see these ideas develop and evolve. And so over time, the hypothesis about there being an attraction between two different masses became a theory because it was well tested and widely accepted. Now, after you formulate your hypothesis, you have to formulate tests to test it. And what you do is you test this. You come up with ideas, and what you're trying to do is find things that are wrong about your hypothesis, not things that are right. Trying to find things that are wrong. You're basically trying to break the hypothesis. So you run your test, you examine your results, and you either accept the hypothesis, or if something was wrong, you modify the hypothesis. Maybe you're just slightly off a little bit, so you remodify the hypothesis, recalculate, redo the test, because you can tweak it just a little bit. Maybe you just were off by a factor or something. Or you reject the model outright, start over again. And this is an iterative process, over and over and over. Now we add to this publication through peer-reviewed journals. peer-reviewed publications. This way, a scientist can put this information out there about their test, about their hypothesis, about what they did, the experiments they ran, and put that information out there so other people can do the exact same test in other locations and see if they can corroborate the results. The more times that test is done, the more it's corroborated, the more likely the idea is to be accurate. And so it moves through the process to becoming a theory. Now, let's step back a moment. Einstein came along and said, yeah, that looks about right, but it's wrong. Einstein said, we need to change the way we think. Basically, that space and time are interwoven as a fabric of the universe. And if you put a mass in the fabric of the universe, that mass stretches the fabric of space-time. So it's not so much that this jar is being pulled down by a force from the planet Earth, but it's the presence of the mass of the planet of the Earth that is pushing the jar down, because space-time is being stretched down towards the center of the Earth. Fundamentally, from a mathematical perspective of the way things work on the macro scale, no real difference between Einstein and Newton at non-relativistic or not speeds not close to light speed. You get really fast or you get really small, Newton starts to break apart. And Einstein's explanation is much better. But generally, if you go and learn in physics class about Newton, or about gravity, you're going to learn about Newton first. And it won't be until you get further on into the study of the science that you find out that Newton wasn't really right. Einstein was. But Newton is still a very good approximation for understanding the effects of gravity to begin with. And the mathematics still actually work. So that's another point about science, is that if you go into the sciences, one of the things you will experience is you will find that in a class like this, you get a lot of the basics. And then as you move deeper and deeper into the subject, you find that, oh, there are things that weren't quite right about what I was told. And that's just simply because you can't be expected to get all of that information all at once, because you need to learn the basics first before you can learn the exceptions to the rules. Now, let's talk about the Earth itself in general. The Earth is relatively small in terms of the nature of the universe and other planets. It's self-contained, and it really is a very unique place, at least in our solar system. We look at the Earth, we divide it up into 4 different spheres of influence, if you will. We have the hydrosphere, which is all the water of the Earth, which is one of the things that makes the Earth very unique in the solar system and possibly the galaxy, with a global ocean that covers nearly 71% of the surface and contains about 97% of all the water on the Earth. We also have lakes and streams. The moisture in the air is clouds or water vapor, which brings us to the second sphere, the atmosphere, which is the gaseous envelope around the Earth. We also have the biosphere, which is all the life on the planet, as well as the solid Earth itself, or what some people call the geosphere. As a system, the Earth is a dynamic planet with its interacting parts and spheres. The atmosphere and the hydrosphere create our weather, with some degree of interaction with the geosphere to cause certain systems to happen in certain ways. Generally speaking, a system is a group of interacting or independent parts that can form a complex whole, such as the weather system, the solar system, the biosystems. The spatial scales on the Earth go from fractions of millimeters, so basically microscopic, to things that are thousands of kilometers in size. The same with timescales. Timescales range from milliseconds or microseconds, nanoseconds, all the way up to billions of years. Now, when we look at it, energy systems on the Earth really are driven by one of two sources. So the first source is the sun. It's an external energy source. So it's energy that's coming into the Earth systems. And it tends to interact most strongly with the atmosphere, the hydrosphere, and the biosphere. The other source of energy is internal heat from the Earth itself. And this basically runs most of the internal processes of geology, as we'll see. It's responsible for mountain building. It's responsible for the volcanoes and earthquakes and deformation. So where did the Earth come from? Well, we start out with what we now call the nebular hypothesis, a cloud of gas and dust in outer space. And something happened. The most likely explanation is a shock wave of some sort from a nearby supernova passed through this cloud of dust and jostled it enough so that it began to clump. There was an experiment by some astronauts on the International Space Station where they took some baggies of different materials. This is for a fourth grade science class that actually was lucky enough to have astronauts do experiments for them in space. And they just shook different materials. And one of them was a bag of flour. When they shook the flour did something interesting. It started to clump. Now, this clumping wasn't gravitational. The particles were too small to really have that strong of a gravitational attraction. What it turned out to be is it was electrostatic, sort of like the dust bunnies under your bed or on the shelf. So it may have been that jostling caused enough of an electrostatic charge differential because of particles rubbing against each other. Take a balloon, rub it against your hair, stick to the wall. To create an electrostatic charge system, and things started clumping on that. Once they got big enough, gravity began to take over, and things began to clump bigger and bigger. This probably happened about 5 billion years ago, and it took a couple of 100 million years for it to process. But then this cloud moved into a disk shape, and this has to do with the way things work in physics when they start to rotate. But the largest mass became what we now today call the sun, and you had a few many smaller masses that eventually agglomerated into the planets and the asteroids, with the large percentage of the lighter materials being in the outer solar system and the inner solar system being made up of mostly heavier materials, because once the sun kicked on, it creates a streaming wind of charged particles that blows some of the lighter materials into the outer solar system and will segregate the heavier materials in the inner solar system. So over time, you had this chunk that grew and grew and grew through what we call accretion. Things would hit it and stick, or mostly stick. Some bits might get thrown off. But over time, this imparts a lot of energy into the system. Pounding, pounding, pounding. If I sat here and just hit my hand like this, besides making a lot of noise for you guys, what's going to happen? Well, and besides my hand getting sore over time, if I do this long enough. If you just do it, you might notice that after 10 or so hits, you start to feel some heat in the hand. And that's because when you have an impact, that energy is being changed. Some of that kinetic energy, that energy of motion, is being converted into sonic energy, the sound you're hearing. It's being converted into energy that's moving through my hand, and some of it's being converted into frictional energy or heat. And so if you can imagine all these particles streaming in and hitting this one body over and over and over, the planet begins to heat up. Once it gets hot enough, then it begins to undergo a chemical segregation. So lighter things are going to float to the top, heavier things are going to sink towards the bottom. And this created the layering that we see within the Earth. And we'll talk about that here shortly. The atmosphere of the Earth probably came about from gases leaving the materials as they got hot enough to melt, as well as sources of other materials being brought in by, namely, comets. But the first atmosphere of the Earth and the original crust of the Earth, long gone. They've been since destroyed by geological processes. So let's talk about the nature of the Earth. And I'm going to try to draw this out for you. You'll see this in your book, but let's try to draw this out as a cut section through the Earth. Now, we can look at the Earth and its layers in two different ways, actually. One is chemical, the other is physical. So, if we look at it by those natures, and I'll try to get this up here. There we go. So we're going to look at it the chemical side first. The chemical side actually basically is 3 layers. So only 3 layers. We have the crust, we have the mantle, and we have the core. Those are our 3 layers. The crust is relatively thin. It actually comes in 2 different types. We have continental crust or oceanic crust. The oceanic crust tends to be very thin, only about 7 kilometers or 5 miles thick. It's composed of a rock called basalt for the most part, whereas the continental crust is much thicker, averaging 35 to 40 kilometers thick, or about 25 miles thick. The upper portion of the crust is granitic in nature, while the lower portion is basaltic in nature. Interestingly enough, though, continental rocks are less dense, or continental crust is less dense than the oceanic crust, which is one of the reasons why it expresses itself higher on the Earth. Now, the crust is a very, very thin layer on the Earth. The mantle is much thicker. It makes up basically 82% of the Earth by volume, and it's basically a somewhat solid rocky shell. There are parts of it that will move plastically or deform plastically or flow kind of like silly putty can flow. It extends down to a depth of about 2,900 kilometers or 1,800 miles. And at least in the upper portion, it's made up predominantly of a rock that we call peridotite. We know this because in very strong types of eruptions of basaltic lavas, it can actually bring pieces of the mantle up with it, and as what we call a xenolith. And so we can actually find those where we have it. I do have a sample in the class building. Don't have it here. So if I can find a picture, maybe I'll try to get a picture up for you guys. Then we have the core. We believe the core is to be a mixture of iron and nickel, mostly iron, 95% iron, 5% nickel, with minor amounts of other elements in it. And due to the extreme pressures it's under, it reaches densities between 11 and 12 grams per cubic centimeter. Keep in mind, 1 gram per cubic centimeter is the density of water. So we're talking about things that are 11 to 12 times denser than water. Now, that's the chemical side. So we have those 3 different chemical layers. Physically, it gets a little more complex. The physical side has 5 layers. Okay, and don't know if we'll be able to see it. 5 layers on the physical side. Some of this is due to the pressure and temperature that the materials are under. Some of it is due to the nature of the actual chemical materials that we're talking about. That's what complicates this a little bit. But we'll go through this fairly quickly. It's not too hard But it is, again, these different compositional layers and well as the physical layers are a testable idea for you guys, and they're really important anyways. So let's talk real briefly about the five main outer layers, or five main layers of the Earth, I should say. The outermost layer is what we call the lithosphere, or the rocky sphere. This is comprised of all of the crust plus an upper portion of the mantle. It's relatively cool and rigid, hence the name lithosphere, because it's rigid like rocks, but it's also brittle like rocks, so it breaks into pieces. On average, it's about 100 kilometers thick, roughly 64 miles, but it can be over 250 kilometers thick under the oldest portions of the continents and at the largest mountain ranges. In the ocean basins, it can be a few kilometers thick. Generally speaking, this is the rigid outer part where everything we know about the Earth from direct observation, physical observation, is found, where we've actually gotten samples from, where we've actually drilled holes into. Pretty much this is the nature of that area. Below that, we get into stuff that we've had to go through indirect means to try to find out about and observe. And we'll talk about those when we talk about earthquakes in the Earth's interior. So the next layer below the lithosphere, which again is about 100 kilometers thick on average, is the asthenosphere. This is what is called the weak sphere of the Earth. It goes down from about 100 kilometers on average to about 660 kilometers. It's weak because it has pockets of material that are molten in it, or what we call partially molten. So because of this partial melting, especially in the upper reaches of the asthenosphere, the lithosphere is literally decoupled to a degree. This allows the crust of the Earth to move, and since it's broken into large chunks or plates, those plates can move around. This is part of what we call plate tectonics. We will get much deeper into plate tectonics next chapter, so I don't want to go too deep into it right now. But we will get into it more next chapter. Below this, from about 660 kilometers to about 2,900 kilometers, is the mesosphere, or the lower mantle. It's more rigid than the asthenosphere. It doesn't appear to have anywhere near any large degree of partial melting within it, but we do have evidence that it moves slowly, very slowly. And then we have the core. Now, the core starts at 2,900 kilometers deep. The outer portion of the core is liquid. It's liquid iron nickel. It's has convective flow within it, and we now have very strong evidence that that convective flow within the mantle, or within the outer core, is what generates the magnetic field of the Earth. And then we have the inner core, which is solid iron nickel, crystalline iron nickel. And we believe that it is strong due to the immense pressure that it's under, as well as that's why it's solid. Also, the interesting thing that we've learned is through different types of studies is that the inner core of the Earth actually rotates about 1 degree more every year than the outer surface of the Earth. So the inner core is actually spinning slightly faster than the rest of the Earth. And when we've modeled that, we created a magnetic system very similar to the Earth's magnetic system. So it's not only the convective nature within the outer core, but it's the fact that the inner core is slightly decoupled that seems to be part of the system. Now, generally speaking, when we look at the Earth, we can look at the surface of the Earth in two principal divisions if we take a very large view of the Earth. We have the continents, the high areas, and we have the oceans, the low areas. The significance between these tend to be based on their relative levels, which in part is due to their compositions. Continents have a prominent feature, a linear feature that we call mountain belts. These are not randomly distributed. We actually have a way of showing why mountains occur where they occur. We see two primary zones of mountains, the circum-Pacific belt, which is around the Pacific Ocean, as well as the Eurasian Himalayan system, which is basically a belt of mountains that run all the way from southern Europe through the Middle East into Asia through the Himalayas. Then we have the stable interiors. These are known as the cratons. These are combined of two different provinces. One is the shield, which are expansive, very flat regions of the craton that are exposing the oldest rocks of the continent. They tend to be crystalline rocks, highly deformed, and very flat because they've been weathered down very flat. So with the continents, we have also the stable interior, also known as the craton. Part of the craton is the shield, which are the expansive flat regions of deformed crystalline rock. This is some of the most ancient rock that makes up the foundations of the continent, and it's exposed because of how much it's been weathered and eroded down. Outside of that, we have the continental shelves, which are areas where you have younger sedimentary rocks overlaying that deformed crystalline rock. And together these create the shields of the continents, also known as the stable platforms. In the ocean basins, you have several different features. You have the continental margins, which go from the shoreline outwards, where the shoreline isn't really the boundary of the continent. That just happens to be where the water level or the sea level is interacting with the continent. The continent extends outwards. Generally speaking, there's what's called the continental shelf, which is the portion of the continent that is actually submerged, and it goes outwards from the shore. Beyond that, you get into the continental slope, which is a very steep drop-off, which is very close to the edge of the continental material. It's basically going to be part of the outer edge of the continent, and then that can either lead into the continental rise, which is where the slope up from the deep ocean basins, or into a deep ocean trench, which we'll talk about here in a moment. Within the deep ocean basins, there are a number of different features that we can see. These are the areas between the continental margins and the oceanic ridges. We see very flat, featureless plains called the abyssal plains. These are some of the flattest areas of the Earth. We have the deep ocean trenches. These are these long, narrow, very deep, for lack of a better word, canyons that sometimes are along the edges of continents. In other places, they're along the edges of island arcs. And they actually mark a location where one tectonic plate is subducting down below another, sort of like this. And so you can see that that would create a deep trench or deep area in between. The trenches are usually going to be located near young mountains and areas of volcanic activity. Almost always that we see that. Then we also have the submarine volcanoes and seamounts. These are volcanic features that have formed. If they are below water, they're submarine volcanoes. Once they're above water, they're volcanic islands. And eventually a volcanic island is going to weather away and erode away and become a sea mount. Beyond this, we also have the oceanic ridges. This is a continuous belt that winds around the planet, some 70,000 kilometers long. It is an area of igneous activity where basically what's happening are the continents are spreading apart, and as they spread apart, or the plates are spreading apart, I should say, and as they spread apart, new continental or new oceanic material is created. should say new oceanic, not new continental. They're composed of igneous rock that's been fractured and uplifted. Their expression of the ridges really depends on how fast are the plates separating, as we'll see when we talk about them later on. Lastly, I want to bring up what's called the rock cycle. The rock cycle is basically a loop that shows that any rock can become any other rock. Generally speaking, when we start out with it, we start with magma, liquid rock. Okay? That magma will cool and crystallize to become igneous rock. Okay? Now, that igneous rock can undergo uplift, weathering, and erosion. And it becomes sediments. Those sediments can undergo burial, compaction, and cementation, part of a process that we call lithification, and become sedimentary rocks. Which can undergo a series of heat and pressure to become metamorphic rocks, which could be undergo heating. Let's shorten that up. Heating and melting and becomes magma, so we close the loop. Now, as I said, any rock can become any other rock. So, an igneous rock, let me try changing colors here. An igneous rock could, if the pen worked, it doesn't. An igneous rock could go straight to heating and pressure and become a metamorphic rock, or it could go back to being heated and melted and becoming magma again. A sedimentary rock can undergo weathering, uplift, and erosion, become sediments once again, and become yet another sedimentary rock, or it can skip over and just go to heating and melting and become magma again and become another igneous rock. And then a metamorphic rock can go back onto itself and become yet another metamorphic rock, as we'll see when we discuss metamorphic rocks, or it can become uplifted, eroded, and become sediments. All these paths for the rocks are valid and various. There is no true point of beginning, so we just use magma as our point of beginning. And we follow the cycle from there. Now, the next class, we're going to talk about plate tectonics. Generally speaking, in the previous book that I've used, this was broken up into 3 different lectures. I'm going to see what I do with this new one. I got to look over the new book and really get a better feel for it. Could be 3 lectures that you're going to look at. But then we'll also have a small exercise I'll have to put together and figure out how to get into the D2L for you. But generally speaking, hopefully that was a brief introduction to geology. You may have noticed a little bit of an issue with the video. I had an issue with the recording. It stopped on me and I had to do another piece and splice everything together. I hope that works. But with that, I'll see you guys in class on Wednesday, the 17th. And look forward to talking to you all then. Have a good night.